Hello. Today I'll be going over techniques to properly read and understand what it is that the runtime tester is telling you. So if we run the runtime tester, you'll see that it might be a little bit confusing. Let's hypothetically say we want to compare our O of n method to our ideal O of n. We can see various O of n methods. They're both much slower than our ideal O of n. So how do we know they're actually running in O of n, especially with these spikes going on? It looks pretty uninformative. Well, there's three sliders here that are going to help us. The first slider I'm going to tell you about is simulation delay. It's really simple. It just changes how fast the graph moves. I make it really small, it's going to simulate very, very quickly. If I make it very long, it's going to take a very long time to simulate. It's going to take 1 second between things. You make simulation delay fast if you want to get more numbers on the screen quicker. You just want it to run faster. Right? That's one thing. Depending on how fast your computer is, you might not be able to simulate at a particularly fast delay. That's useful because we can see that the trend, none of these are going to like shoot up. These spikes can be ignored because that's just the computer struggling to keep up. So now if we refresh it, and we can show you the other one. This is called step time. Step time affects mathematical methods. So here it affects the green method, and it changes the slope of the O of n. So it's still going to be an O of n, but it's going to have a bigger slope. So here it's become a much bigger slope, so now it's truly upper bounding our equations. This slider essentially just affects the slope of ideal mathematical expressions. If I put it somewhere around 519, that should be roughly accurate. It depends on the speed of your computer. It's just telling you by how much time does each step take. That's why it's step time. So for the mathematical step, it calculates the duration of each theoretical step in nanoseconds using a mathematical expression, and this is roughly what it's doing. This is changing the slope. So now we can truly upper bound our functions with O of n and see that they are indeed both faster because they increase less quickly. But if we really want to prove it, there's the third and the most useful slider. It's called steps per iteration. If we crank the steps per iteration, we can see how our different functions spike up. Our O of n, our ideal O of n, is the yellow. Our multiply polynomial is the orange, and our add term is the green. So you can see that this one is going much less increase than O of n. And for that reason, it's better. If we also put on O of n squared, we just want to compare it to O of n squared, we can see that O of n squared increases so much faster once we turn up our steps per iteration than everything else. Everything else looks like a flat line. The way you get this is you turn the steps per iteration way up. Imagine in math, you're taking the limit as this approaches infinity. That's essentially what cranking the steps per iteration does. It's cranking the numbers so high that you can really tell the difference between the different efficiencies. So you want to max out your steps per iteration to see O of n squared here runs away from it. If we try O of n log n with maximum steps per iteration, we can also see that O of n log n runs away from it. Right? So all of these other sorting efficiencies run away from it. O of 1, well, let's see what happens with O of 1. Oh. And they are running away from O of 1. This one, it was crashing down, but it's going to spike back up. They are like astronomically higher than O of 1. Hopefully you can see that. And then if you compare them to O of n, they're not really astronomically different from O of n. Overall, though, we can see that none of these are really, truly stratosphering away. They're like still both visible at the same time. Whereas if we put O of n squared on here, it's going to go into the stratosphere, it's going to escape, and that's going to just show us that O of n squared is a lot slower. So that's kind of how you compare graphs, how you're supposed to compare graphs. I wouldn't put too much stock into what's higher or what's lower, really. I would put stock into how the different rates of increase are visible. That's the sort of point of the tool. Yeah, and the useful sliders are, again, steps per iteration. That's the most useful. You crank that high if you want a better trend. Step time, you can adjust mathematical methods like their slope. Simulation delay, you can adjust how fast it tries to run. Good luck.